record on this computer. Okay, so we're recording now. So I'm going to review some of the things that I said about Fourier series because they're so important. And also I'm going to drill down on one of the topics in the very beginning of the chapter on Fourier series. So, oh, wait a second, there's a question here. All right, there's a question about equation 1.26. All right, so I'm going to first answer the student's question, and this is the linear least square. That's what I thought it was. There we go. I rather like linear least squares, by the way. Anyway, we're talking about equation. Well, let's see. I apparently changed the numbering, damn it. 250. All right. So what we want to do is we want to minimize this. So we take the derivative with respect to, we're looking for x. And so we take a derivative with respect to an arbitrary x. Now, the reason I did XL is that the XK is already in the sum. And so if we differentiate with respect to XL, then what we get is we get the minus AIL here. So it's just a question of what we mean by the various indexes. So, you know, I mean, I could have called that instead of L, I could have called it J or P or something. But I wanted to keep this structure. I didn't want to change what K meant. K is the index of the sum. Well, when you differentiate with respect to XL, the coefficient of XL is AIL, not AI something else. It's not AIK, it's AIL. You differentiate. In other words, there are a bunch of Ks here going from, K takes values from, wow, what is that? K takes values between 1 and n. And let's see, I've got a feedback going on here that is serious. I think it's because I'm using QuickTime to project the iPad screen onto the iMac like this. And I think what I have to do is I have to mute this. So, well, that's about as low as it can go. So let me put this back here. I'm not sure. Oh my goodness, we've got Chef Boyardee here. Oh, Keanu Reeves' dog, Jesus. Okay, all right, let's, so I hope that that's, okay, we've got also a homework question. What is the homework question? What are we solving for in problem 135? All right, let me jump to the exercises here. Well, what you need to do is you need to substitute this expression for the Hamiltonian and then evaluate the density operator and its entropy. So that's what you're trying to do. Okay, now let me try to go to the Fourier series again. And now, for Fourier series, as I said to you on, I guess it was Tuesday, these three equations are really the 90% of what you need to know about Fourier series. It's that these phase functions are orthogonal, or in fact orthonormal with the square roots. They're orthonormal on the circle. You can expand a wide class of functions in terms of these phase functions or phase factors. And the orthonormality of the phase factors gives the nth coefficient as the orthonormality projects out the nth coefficient as Fn. And so those are the basic things, and you really ought to think about these three equations deeply and understand them. So that's really important. Now, after that, I did some Dirac dance here, and I think it was a little too cute. And so let me instead jump forward in the book and explain what lies behind equations 3, 4 to, I guess it's 311. Well, right, up to 3, 4 to 311. What's behind those equations? Let me jump forward to the Dirac delta function section. So once again, and let's go down to this part right here. Remember, I said equations 3, 1, 3, 2, and 3, 3 are the important equations. They're 90% of what you need to know about Fourier series. The other thing you need to know is something I'll just tell you now and tell you again later, namely that the class of functions for which this works is all functions that are square integrable on the interval. In this case, the interval 0 to 2 pi. So if we take the formulas 3, 2, and 3, 3 and put them together, what we get is this is the formula, in fact, that might even, yeah, this is the formula 3, 2. And then formula 3, 3 tells us what Fn is. Fn is this integral f of y dy e to the I n x over square root of 2 pi. Now, if we assume that there are no convergence issues, and we just, or equivalently, if we assume that the function f is in a class of functions that are suitably smooth and go to 0 at infinity suitably rapidly, then we can certainly interchange summation and integration. And this equation turns into this equation. And we have that f of x is the integral from 0 to 2 pi of f of y dy multiplied by the quantity in parentheses. And this quantity is an infinite sum of these orthonormal phase factors actually divided by an extra factor of square root of 2 pi. And these factors here are periodic with period 2 pi, these factors. So it must also be true that f at x plus 2 pi L is equal to this, where here what is meant on the left-hand side is the periodic extension of the function f. So if f is not only a smooth function, but also a periodic function, then this equation is literally true because these factors are periodic. If, on the other hand, f doesn't cooperate, is not periodic outside the interval 0 to 2 pi, then on the left-hand side, we need a little p here as a subscript. And what we're talking about here is the periodic extension of f. Now let's look at this equation. This is a remarkable equation, which once again, it was Dirac who pointed this out. And the implication here then is that this is not simply a Dirac delta function, but it's an infinite sum of Dirac delta functions. And this is in fact called the Dirac Comb. And that's because what we've got is a bunch of Dirac delta, in fact, infinitely many Dirac delta functions. So in other words, if you look at this, what you see is that this is something that has spikes when x is equal to y plus 2 pi L. And that then projects out f of y plus 2 pi L. I'm sorry, when this thing as a function of y has spikes when when x is y plus 2 pi L. And so so this gives us f of x plus 2 pi L. Okay, so another way of writing this is you separate out the n equals 0 case, and that's 1 over 2 pi. And the other cases, you can combine the n equal to the positive n with the negative n, and you get a cosine. And the 2, in fact, helps give you that cosine. And here I've set y equal to 0. We get this as the expression. And if we stretch, if we consider an interval that's of length capital L, then we get this expression. I use MATLAB to illustrate this numerically. And what we've got here is the first 100,000 terms of this cosine series, this thing here, plotted on an interval from minus 15 to 15. And we get Gibbs overshoots at the discontinuities, and the integral, of course, has to be 5 because there are 5 cases where this delta function can be non-zero. So let me just show you the cosine. Here's the cosine series for the Dirac Comb, and what I want to call to mind here is that this is x from minus 15 to plus 15, and this is minus 2 pi, minus 4 pi, 0, 2 pi, 4 pi. Notice, however, that the y-axis is scaled. In other words, this point here is about 3.2, say, times 10 to the 4th. So it's not of the order of 3, it's of the order of 30,000. And so that's what these spikes are like. And if we had infinite resolution, we'd see some jaggedness here. And this jaggedness is the Gibbs overshoot there. In the limit of infinitely many terms. And we have something such that if you, okay, what's the meaning of this? The meaning of this is that this sum here, if f is smooth, when you integrate f of y dy, what you get is f of x, and because this thing is periodic, you also get f of x plus 2 pi L. But so what I'm saying is that in you might worry, well, what about these Gibbs overshoots? Well, the Gibbs overshoots are of such high frequency that they cancel absolutely in the limit for functions that are in functions f that are smooth. So I hope that what I've done is made this thing a little bit clearer, but I have right now the sinking feeling that I've made these even more difficult. Yes, there was a question about the Gibbs Overshoot. Yes, I tell you what, why don't I go back to where we left off in the Fourier series. So let's go back to the beginning. So these are the really important aspects. And then as I go forward, I'll get to the Gibbs Overshoot again. So the Fourier series, as I said, if you have a square integrable function, then you can expand it quite accurately as an infinite sum coefficients. The coefficients are given by these integrals, and these phase factors are orthonormal, in fact. So as I said, you can now interpret that in Dirac notation this way, and well, all right, let me actually skip that. We went through on Tuesday that the complex conjugate of the Fourier series clearly is you complex conjugate these and you complex conjugate the phase factors. So that's equivalent to, you can, if you change the notation here from n to minus n, you get a minus n here and a plus n there. And so that tells you that the nth Fourier coefficient of f star is the minus nth coefficient of f. And if the function's real, then we have fn is equal to f star of minus n. And so that's this equation if the function f is real. Okay, now this is just a quick review, so let me skip that. The interval can be any interval of length 2 pi. Where you put the 2 pi's, well, you can decide where you want to put them. If you want to really avoid mistakes, then you stay with the formulation here, 3, 1, 3, 2, 3, 3, and you'll be fine. If, on the other hand, you're tired of having square root of 2 pi's all over the place, then you can use these expressions. The important thing is that you've got a whole factor of 2 pi somewhere. And this is an example that we did on Tuesday. Okay, let's go now to real Fourier series for real functions. This is where most books on Fourier series start, but I think this is harder than the approach with complex numbers. And uh-oh, I just noticed I don't see the boundary anymore. Okay, we have an issue here. Something happened. You want screen sharing. Let me just make sure. Where is this screen sharing? Right. And normally there's a green border for screen sharing, and I'm a little worried that I don't see. So desktop 1, share. And normally I see a little green okay, so you say we are sharing the screen. All right, that's good.
Because from experience here, I'll get that text at 8 a.m. and they won't be delivered till like 7.
Wait, I don't quite understand. Could you say it more clearly, slowly, and louder? Can everybody see the screen? Okay, I get a yes here. I'm getting a bunch of yeses. All right, so somehow it's okay. All right, so let's go to real series. Now, as I said, because the function f is real, the Fourier coefficients obey this rule, which is that the coefficient of for minus n is the complex conjugate of the coefficient for n. So first we will write the Fourier series this way: the zeroth term, the positive n terms, and the negative n terms. And then changing minus n to plus n or n to minus n, we can rewrite this term as that. And now we know that d minus n is dn star. So we go over here. And now we expand e to the inx, this famous formula that is quite remarkable. So we expand e to the inx as cosine nx plus I sine nx, and e to the minus inx is like that. We combine the two cosine terms and we have this, and we combine the two sine terms and we have that. Now notice that these combinations are actually real, and we call them an is dn plus dn star, and bn is idn minus dn star. And so we have our formula for the Fourier series of a real function. It's an a0 over 2 plus an cosine nx plus bn sine nx. And an is given by this expression. And if we realize that f is real, we have this expression. This is a cosine, so we get that. Bn is this expression, and so it's a sine. And so those are our formulas. So for real functions, the equations are f of x is this sum for real functions, an, bn, a0, they're all real. An is given by this expression. It's a cosine integral. Bn is a sine integral of f. Okay. You can also derive them from the orthogonality of the sines and cosines. And if the function is periodic with period 2 pi, you can choose any old interval and you'll have the same Fourier coefficients and so forth. If the function is not periodic, then the Fourier series depends upon what the interval is, and you get a different Fourier series in each case. Or you may get a different one in each case. In general, you do. As an example, maybe the Fourier series for x squared, it's even. So the sine coefficients all vanish. Here we're choosing the interval from minus pi to pi. And why that? Well, because of the symmetry. The cosine coefficients then are this, and doing the integral, we get that. A0 is this is the sum, and it converges very rapidly within the interval. On the other hand, at the endpoints, it doesn't do as well. And we can look at the graph here. The x squared is the solid function. The Fourier series of 7 terms is dot dash, and you see there's some difference here. And the Fourier series for 20 terms is just the dashes, and you see that's really good. And I couldn't go beyond 20 terms because we couldn't see the difference between the function and between the series and the function. They'd be too close, and we couldn't see them on the screen. Here we're just doing we're plotting x from -1 to 1. If we, and it converge, and in that subinterval, it converges, of course, very well. As we get, though, to if I plotted from minus pi to pi, there would have been some jagginess at the endpoints. And then, of course, the thing is not periodic. And so the Fourier series would have gone up and then it would have gone down. So it would have repeated this pattern periodically. And that gets us to the Gibbs overshoot. So as another example, suppose f of x is x on the interval. It's obviously not a periodic function. On minus pi to pi, it's an odd function, or actually x is obviously an odd function. And so we use minus pi to pi to get a simple Fourier series. The cosines terms all vanish. So we do the sine integrals, we get this. And so in figure 3.4, I plotted this series, and this is what it looks like. From minus pi to pi, it does a fairly decent job for the dotted curve is 10 terms, and the solid curve is 100 terms. The solid term is this one here, and that's 100 terms. And inside the interval, it's going to give a very good approximation as you go beyond 100. You go to 1,000 or 10,000. But you've got, because this is a function that's not periodic, you've got a conflict between the periodicity of the sines and cosines and the aperiodicity of the function x. And so you get jitteriness here, and the function, the Fourier series goes too high here, it goes too high there. And if we look at this more carefully, then what we see at pi, the 100-term series is off by that much, and the 10-term series is off by even more. And this is called the Gibbs overshoot. So you can read that yourselves and watch the movie somewhere by yourselves. I'm going to skip that because I'm supposed to be teaching math, not social science or history. So if we, let's see, there's right, the overshoot is the difference between the Fourier series and the real function. And for functions that are not periodic, at the endpoints, you're going to get trouble. And so the fit is and you see this fit as if we went to much higher, a higher number of terms instead of 100. If we went, well, first of all, notice the periodicity of this thing. It's sort of a slow, with 10 terms, the periodicity or the frequency at which the approximation occurs is like that. But as you go to 100 terms, it's 10 times higher frequency. And as you go to 1,000, 10,000 terms, what happens is that the overshoot is positive here, it's negative there, it's positive here, negative there. And so if the function's at all smooth, it cancels. And in particular, if it's a square integrable function, which need not be smooth, nonetheless, it'll come out to be, you'll get the right answer for an integral. Stretched intervals. Suppose we go to length L instead of 2 pi. Then we use different phases. These are the orthonormal phases that we use, either the 2 pi I mx over L, and we divide by square root of L. And they're orthonormal on this interval 0 to L. And the Fourier series then looks like this. And let me just make this a little bigger for you. And the Fourier coefficients look like that. So once again, the key formulas are this one, that one, and this one. So those are the formulas you need to know. As I said, it's 90% of the Fourier analysis. What we'll see in a moment is that the sum of the absolute value squared as the coefficients is always equal to the integral of the absolute value squared of the function over the interval. And you see, this is why it is that Fourier series work for functions that are square integrable. You see, this thing is then finite on the right-hand side, and this is finite. And we'll derive this later today. Or if not, next Tuesday. If the function is periodic with period L, then f of x plus NL is the same thing as f of x. We can shift the domain of integration by any real number, and so we could change this formula to that formula, no problem at all if it's periodic. And an obvious choice is the interval minus L over 2 to L over 2. And so then we have these two formulas for the Fourier series. So the Fourier series, I said there were three important equations. It's really two equations that are important. The orthonormality of these phase factors is obvious if you know how to integrate to a definite integral. If the function f is real, then on the interval 0 to L, what you have are these expressions. There's our Fourier series, and the ANs and BNs are the cosine and sine integrals like that. And the orthogonality relations are these ones, and they go on the interval 0 to L. But you get L over 2, you're not getting 1 there. Now, very important for physics is Fourier series of functions of several variables, because we live in three-dimensional space with also a time dimension. So on an interval 0 to L, the ordinary series, Fourier series formulas are the ones I just emphasized. Let me just make a note. We can go to m dimensions, x1, x2, xm, and a dot product like that. Then f of x will be a sum on all these integers 1 through m, and we'll have f sub n, where n here is m is a vector of m integers, and we'll have e to the I 2 pi n dot x over L, and L will be raised to the power m over 2. And the functions, the coefficients are given then by an m-dimensional integral with the complex conjugate of the phase factor times the function. What I might do to make this a little bit more transparent is to show you what this looks like for the case of two variables. So let me go to two variables, and just so I get the phase factors more or less right, let me leave that there, put that there, and go here. So suppose we were doing m equal to 2. Then we would have, in fact, we'd have something like this. F of x and y would be equal to a sum on n, and let us, well, n1 and n2, let us say, or nx and ny, maybe I'll say that. nx and ny, e to the I 2 pi, and it would be nx times x plus ny times y divided by L, and we'll divide by, oh damn it, I'm supposed to be doing this equation, and I sort of am, but down here what we'll have is L, simply L, because M is 2 in this case, and then F sub nx ny would then be an integral dx dy of, in each case, from 0 to L. And we would have e to the minus I 2 pi, and it would just be nxx plus ny divided by L, and we'll divide by L again, and we'll have f of x and y, and of course I left out the key thing here, f sub nx comma ny. Okay, so I hope that makes things clearer. You can take this yourselves and derive that yourselves and see if it doesn't make sense to you, or better yet, go to the three-dimensional case x, y, z, and you'd have nx, ny, and z, and so forth. Okay, so let me now go on to this topic of integration and differentiation of Fourier series. What happens if we integrate or differentiate a Fourier series? Well, suppose we integrated both sides of this. Then we'd have the integral from 0 to x of this thing, and we'd have to integrate this series. And if you, whoops, I don't know what's going on with this mouse. The slightest movement and it changes drastically. Anyway, if you do the integration, and I hope I did it correctly, what you have an x here, but here you have fn over n, because you're integrating this phase factor, and the coefficient of x has an n, and so you get an n in the denominator. And that means that the series converges more quickly. So basically, an integrated function is smoother, and its Fourier series converges better, or converges more rapidly. On the other hand, if you differentiate the same series, you get this expression, because when you differentiate e to the 2 pi I n x over L, you pull down a factor of n, and that means the convergence is worse. And so if a differentiated function is rougher and its Fourier series converges worse or less well. Now, here's some mathematics, and I'm sort of assuming that everybody had some math courses in college taught by actual mathematicians or careful physicists. So let's just go back to what we're talking about. What we mean here by a Fourier series is that we're representing the function as a limit of functions f sub capital N, which are the Fourier series from minus n to plus n, and little fn is given by the same standard formula that we've seen many times. Now the Fourier series is always periodic, as I've said, and so if the function's not periodic, then the Fourier series always represents the periodic extension of f, so that f sub the periodic extension at x plus nl is just f of x. Now, here's the standard math definition. A sequence of functions converges to a function f of x on a closed interval. Closed interval means the endpoints are part of the interval. If for every small number epsilon, there exists an integer such that the difference between the exact function f of x and the approximation f sub n of x is less than epsilon for all n greater than n, and this n is depending upon how small we require how good we require the approximation to be, and the particular value of x. So this is an n that depends on two variables. Now, of course, it's much nicer if you can say that this is true for n greater than n of epsilon rather than n of epsilon and x. And in that case, we say that this function, the series of functions, not only converges, but it converges uniformly on the interval. So if n is independent of x, then it's uniformly convergent. A function is continuous on an open interval, and an open interval means we have x between a and b. If for every point, the limit as the argument of the function approaches x from below, which is to say, we define that as f of x minus 0 is this limit. F of x plus 0 is the limit from above. If these two limits agree, so f of x0, in fact, what I probably should have done is I probably should have put this over here, and put an equal sign. So let me just make a note to that effect. If f of x also, if the limit from above of the point is equal to the function at a, and if the limit from below is equal to the function at b, then f is continuous on the closed interval. And now it's functions that are continuous on a closed interval, particularly nice because you can show that they're bounded and integrable on that interval. Integrable in the ordinary Riemann sense. So now, if you have a sequence of continuous functions, if a sequence of continuous functions converges uniformly to a function f of x on a closed interval, then we know that the error is less than epsilon as long as n is sufficiently big. And so we can say that the difference between these two integrals is less than or equal to the integral of the absolute value of the difference, and that's less than epsilon times the, and if you multiply by the length given by dx there, you get b minus a. And so as epsilon goes to 0, these two things are equal. So if you have a uniformly convergent sequence of continuous functions on a closed interval, you can integrate term by term. That is to say, the limit of f sub n is the same thing as the integral of the limit of f sub n, and both are equal to the integral of the function that's being approximated. So if a Fourier series converges uniformly, term by term integration is implicit, and that's what I was doing in various examples. But of course, you've got to keep in mind that if you're dealing with something that, with a function that's not piecewise continuous, that's not that, what shall I say? You always have to worry if the function isn't continuous on the closed, or if the sequence, if you have a sequence of continuous functions converging uniformly, great. Otherwise, you have to worry a little bit. Now, let me define piecewise continuous, and it's of course what it says. It's piecewise continuous, function is piecewise continuous on a closed interval a to b, if it is continuous there except for finite jumps from x minus 0 to x plus 0 to finite number of points. And at such points, we define the periodically extended function f sub p to be the average of the two steps in the jump. Okay, here is Fourier's convergence theorem. We're not going to prove it, but I think it's worth certainly stating so we know what's going on. The Fourier series of a function that is piecewise continuous with a piecewise continuous first derivative converges to its periodic extension. So that's the first thing. The Fourier series of a piecewise continuous function with a piecewise continuous first derivative converges to its periodic extension. And the convergence is uniform on every closed interval in which the function is continuous. So since it's piecewise continuous, you've got that it is absolutely continuous on a finite number of intervals that together, apart from the endpoints, make up the whole interval. And if the function has no discontinuities, so in other words, it's a continuous function, then the convergence is not only uniform, but absolute, which means the absolute value converges. So we'll have illustrations of that momentarily. Now, here's a definition, class CK. A class CK is a set of all functions whose kth derivative is continuous. So that's what CK means, continuous kth derivative. And clearly on the interval, the Fourier coefficients are going to be this. But now if we say that it's both periodic and CK, then you can integrate by parts, and what you get is that f sub n is, of course, this derivative. In other words, if you do the differentiation, the first term gives you this, which cancels, and then the other term, differentiating the exponential, you get this original expression. On the other hand, if it's periodic, then this term vanishes, and all we have is this term. The minus signs cancel. And so you can say, if a function's periodic on in CK, then f sub n, the nth coefficient, is not only the integral of the function, but it's also, it's 1 over in times the nth coefficient of its derivative. And if you integrate by parts k times, you find that the nth coefficient is 1 over in to the kth power times the Fourier coefficient of its kth derivative. Or equivalently, it's the integral from minus pi to pi in minus inx in to the kth of the kth derivative. And now the derivatives, the nth derivative of a CK periodic function, of course, is also periodic. And if the k plus first derivative is piecewise continuous, remember f is in CK, so fk is continuous, but fk plus 1, the k plus first derivative, may only be piecewise continuous. May have, in other words, it may, instead of looking like that, it may go boop, 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 and so forth. Since k plus 1 is piecewise continuous, you can, when you integrate, when you do this, you can integrate this by parts, and here you get the piecewise continuous function. And this one still cancels, but it's a piecewise continuous function, so this integral exists. And now you can go, and now fk plus 1 is piecewise continuous on the interval. It's bounded there, an absolute value by something, because remember, piecewise continuous means that it's continuous on the closed interval apart from a finite number of finite jumps. So if you have a finite number of finite jumps, it can only get so high. And so it's bound, so this thing is bounded by, let us say, m. And so the Fourier coefficients of a ck periodic function with whose k plus first derivative is piecewise continuous, they're bounded by something over n to the k plus 1. So the convergence of the Fourier series is better. And you can even go further because this function is piecewise continuous. And in most examples, in other words, this is a function you can write down as in terms of other functions that we know about, then it's almost always true that the piecewise continuous periodic function actually is piecewise continuously differentiable between its successive jumps. And in this case, fk plus 2 is a piecewise continuous function plus a sum of a finite number of delta functions with finite coefficients. And so then you can integrate once more by parts and you get this expression. Namely, after integrating by parts, you get k plus 2, the piecewise continuous value plus these various jumps. And these jumps, it's only a finite number, they're bounded, this is bounded. And so what you have is basically that the Fourier coefficients of a ck function are often bounded, typically are bounded by n to the k plus 2. And we'll see examples of that in what follows. As an example, let's just look at a C0 function. So this is a function that has no continuous derivatives, but it is piecewise continuous. It's continuous. On the other hand, its first derivative is piecewise continuous, but not continuous, so it's not in C1. If you compute the Fourier coefficients, you get this, and you find that if you look at the equation 369, and that tells you that since n is 0, that it's at least bounded by 1 over n. But on the other hand, if you use this bound, then it's 1 over n squared. And in fact, we find that it's 1 over n squared. So we get the coefficients are bounded by this stronger inequality, and this means the series converges. We have a C1 function, for example, 1 plus cosine of 2x. And now I'm just saying that that's the function for x less than or equal to pi over 2, and then it's 0 for x greater than or equal to pi over 2. So now this has a periodic extension that's continuous with a first derivative and a piecewise continuous second derivative, and its coefficients, again, satisfy both inequalities. Now you might say, well, what about, what would be true if instead of imposing these discontinuities at x equal to plus or minus pi over 2, we made the function continuous from minus pi to pi? Well, then we'd have an integral, the fn would be an integral from minus pi to pi of this integral, of this function. And that's what I did up here. You just wind up with 0. And so the coefficients are 0, but I notice here that we've got a bit of a problem here that I think I was too careless in doing this. you have here a 1 over n, and if n is 0, then this is not good. And here, if n is equal to 2 and n equal to -2. So this formula is true except for those particular cases, and I should have done the thing more carefully for those cases. So basically forget about that. I was just sloppy. Anyway, the actual values of these coefficients done carefully is this, and we see indeed that it's a C1 function, but we've got convergence like C cubed. The Fourier series for cosine of mu x. I think I'm going to skip this example. If you want, we can do it to, next Wednesday. And but let me give you the application of these two examples. The application is that these are you get an infinite product formula for the sine and for the cosine, and that's quite interesting, I think. In fact, infinite products are kind of related to path integrals. In any event, I can go through this next Wednesday in detail if you want. And also next Wednesday, I can go through measure and Lebesgue integration in more detail. I think it's explained here clearly, but let me just go a little bit further here and get to the theorem that I wasn't going to do in detail. I wasn't certainly going to prove the theorem, but Rees and Fisher proved this theorem. So suppose that the Fourier coefficients converge. That is, to sum of the absolute value of the Fourier coefficients is finite. Then there's a function f that's square integrable, again in the sense of Lebesgue, which is a more natural definition of integration, but it's a bit of a long story. Maybe we'll have time to go back to it today, but let me go a little bit further now with the standard stuff. So if these coefficients can have absolute values that converge, the absolute value squared to converge, then there's a function f that's square integrable in the sense of Lebesgue on the interval, and it's square integrable, which means the integral is less than infinity, and the Fourier coefficients are given by the standard formula, and the series f sub n given by this converges in the mean to the function f of x, which means that the integral of the absolute value squared of f sub n, this truncated series, converges in the mean as n goes to infinity. In the mean means that the integral of the absolute value squared of the truncated series minus the function integrated, absolute value squared integrated from a to b, that goes to 0. And moreover, the limit of this the limit here, in other words, f of x, absolute value squared, is the sum of the absolute value squared as a coefficient. So this is an equation that that I mentioned in the very, very beginning when I was sort of using Dirac notation somewhat, perhaps a little too loosely, or a little too quickly, certainly. So one of the reasons why people love Fourier series is that they can represent a much wider class of functions than those that are continuous. So if a function is square integrable on an interval, then its n-term Fourier series will converge to the function in the mean in that sense, and that's really why it is that we like them. Let me just see what move this over here, and let's see what other things we've got here. All right, I think we have time to do some quantum mechanical examples. So suppose we have a particle of mass m that's trapped in an infinitely deep one-dimensional square well with this potential energy. The Hamiltonian operator looks like this, second derivative squared plus v. Planck's constant, which is a small 10 to the minus 34, basically joule seconds. So that's energy times time. That means that's what we call action. And Planck's constant, as you know, sets the scale at which quantum mechanics becomes important. When the action is much bigger than h bar, typically quantum effects aren't really important. But when the action is small compared to h bar, they're almost always very important. Okay, but this is a rule of thumb. There probably are exceptions. Okay, so an eigenfunction of the Hamiltonian satisfies this equation. H on the function gives the eigenvalue times the function, the eigenvalue being the energy of that state. And if it's an eigenstate, that eigenstate, I should say. And so what we want is that inside the interval between 0 to L, we have this equation because the potential is 0 from 0 to L. But on the other hand, outside the interval, what we've got is an infinity here. And in other words, V is infinite. And so we have this equation with infinity for negative x and x bigger than capital L. So basically, our solutions with finite energy must vanish outside the interval. And we want to find solutions of the first equation that satisfy the boundary condition. They vanish at the endpoints of the interval. And in between, they satisfy this equation. Well, you can see the solutions are just sines of pi and x over the interval L, and psi equal to 0 outside that interval. And when you take this function, insert it into this equation, you differentiate this function twice, and you get a pi n pi over L squared times the function. So that's the energy eigenvalue is just n pi h bar over L squared over 2m. So it's a 2m here. So what I'm showing here is suppose we start with a wave at time 0 with a wave function that is not an eigenfunction by any means, but in fact is just a function that is 0 outside this interval. And so let me go back to this particular case here. What we're saying was 0 for I mean 0 if the wave function is 0 if x is negative or bigger than L, and all right, I think this must be a different example here. All right, forget 3, 5 for the moment. These eigenfunctions, namely the sines, are complete in that they span the space of all functions that are square integrable on this interval 0 to L and vanish at the endpoints. And they provide for such functions a sine Fourier series. And that's periodic with period 2L. And it's the Fourier series for a function that is odd on this interval and 0 at both ends. So now let's do the time evolution of an initially piecewise continuous wave function. And so at t equals 0, we assume the function is confined in this way. Okay, so what I did was I took L equal to, so this is from 1/2 to 1.5. And so I took L equal to 2. And so that's from 1/2 to 1.5 and 0 otherwise. So this is the initial wave, the wave function, not an eigenfunction, but the wave function at time 0 then is this function here. And the actual eigenfunctions are orthonormal on the interval. The coefficients of the Fourier series then, here's the Fourier series for the initial wave function at time 0. They're inner products of the eigenfunction with the initial value wave function. They're this integral, and they're proportional to 1/n. So then what I did was I plotted 10-term and 100-term Fourier series for the interval. And what we see here is that the 10-term is this one here, and the 100-term is a more accurate representation of the function, but the Gibbs overshoots still occur, but they're less in the 100-term case. Now we can then ask, how does the wave function psi of x and 0, how does it evolve when time? And the way it evolves is you hit it with e to the minus I h t over h bar. And the way to do that in Dirac notation, let me see if I can, wonderful, I can clear that away. All right, let me show you this in a little more detail. So I'm going to put this screen over here. Whoops, I don't want to cover what I'm trying to show you. So what is psi of x and t? Well, this is going to be, this is the inner product of x with the function, let us say x, I'm sorry, the function psi, the state psi at times t. And now we insert here a complete set of eigenstates. And so we have xn, n psi of t. And actually, I didn't actually want to do this. So let me skip that step. So forget that for the moment. What we have here is x e to the minus I h t over h bar times psi at 0. And now we insert the complete set of eigenstates, energy eigenstates. We have e to the minus I h t over h bar n psi comma 0. The eigenstate n is an eigenstate of h with eigenvalue en. So this, oh hell, you're not seeing this. Hold on. This then is equal to a sum on n of x n psi comma 0 e to the minus I en t over h bar. And what are these things? Well, this is the Fourier coefficient, sine Fourier coefficient of the initial wave function, and then these are the eigenfunctions. And so now, that's what I've done then is derive this equation where I've replaced, in other words, xn is sine of pi n x over L apart from a factor. And this one here is this funny, this is the nth Fourier coefficient. So that's that, and this is roughly that. So if we go back to here, what we have then is that this is the expression for, this is the wave function at time t, and it's given by this sine Fourier series. And so what I plotted was the probability that the particle would be at x at time t. And I did it for a 1,000-term Fourier series, and I did it in at time 0, which is the thick curve. The thin term is time tau, which is 2ml squared over h bar, and 10 to the minus 3 of that is the medium curve. And that is this expression here. So that's a frightening, portrayal of, and what is this telling us? Now, you might say, oh my God, that's telling you that quantum mechanics is just infinitely complicated and that anything we ever saw was a lie. Well, no, the craziness here is that I started with a wave function that was discontinuous at x equals 1/2 and discontinuous at x equals 3/2. A discontinuity in a wave function means you've got infinite momentum at that point. And so that's a wave function describing a particle that has basically infinite, it starts out, it's between 1/2 and 3/2, but it's got infinite momentum in it. So as time goes on, it's going to just bounce all over the place. And so at tau over 2, it's this curve, this crazy curve here. And at tau, it's this thin curve that's just doing all kinds of crazy things. Okay, all right. I think that's basically what I wanted to show you. We've got a few minutes left. Is there a quick question or even a slow question? All right. Seeing no question for the moment, let me go over here and start with take the wave function at time 0 to be a continuous function. So now we've got this continuous function between 1/2 and 3/2 and 0 otherwise. And at x equal to L over 4, it's 0 and then it stays 0. So this is a continuous function. Well, if we compute the Fourier coefficients of this continuous function, we get something whose time evolution is much more pacific, much more peaceful. The nth Fourier coefficient is this. Doing the interval, we get that. So the coefficients, the FNs are the coefficients of the initial continuous wave function, and they are ones that go down as 1 over n squared, so it's a convergent sequence. And as it evolves with time, it looks like this. And what do we have here? We have time 0 is the thick curve, And then as you go to 10 to the minus 2, 10 to the minus 1, finally up to tau and 10 tau and 100 tau, you get progressively different wave functions. But what is this telling us? What's this telling us is, tells us is that the initial particle had a probability distribution like this, but as time went on, it leaked out. And what does the potential tell us? Well, in this particular potential, the potential was that it had to be between 0 and let us see what this was originally. I forget whether it's L over 2 or what. What did I say here? It's a 0. It just from 0 to L is where it can be. And so if L is 2, then if L is 2, then it has to stay within the interval 0 to 2. So as time goes by, it remains 0 at the two endpoints, but it spreads out from its initial position, which is between 1/2 and 1.5. It spreads out in this way, and that is something that's more or less what one. That's a reasonable. In other words, this is the kind of quantum mechanical evolution that you can think of as a textbook example, whereas the previous one that had infinite momentum in it, that's a nightmare example. So we're basically at the end. Are there any more questions? By the way, I'm thankful here to Alicia, who's she's an IT expert at UNM, and she is the one who showed me how to use a whiteboard with Zoom from an iPad. And so this is what I wanted to do all along. And yeah, you can even make it smaller. That's what I should have done earlier. Okay, any further questions? No. Well, remember that I skipped a couple of things like a discussion of Lebesgue integration and something else that I think I skipped over. But anyway, we have a problem session coming up on Wednesday. We can do it then. Or if you really want to hear about Lebesgue integration, send me an email and I'll do it on Tuesday. All right, well, I'll say goodbye to you all now, and once again, urge you all to be very careful. In particular, for God's sake, stay out of bars. And in fact, even indoor restaurants are sort of dangerous. Let me mention one thing, though, that does make a difference. We have two forms of air conditioning in New Mexico. The old-fashioned New Mexican swamp cooler, which takes advantage of the low humidity here and blows hot air from hot, dry air across a wet screen and then into the house or into the building or office. And then you have to, of course, leave a window or a door open, and then the air blows out. These swamp coolers make buildings and offices and homes and restaurants and stores safe, pretty safe. I mean, not really safe, but a hell of a lot safer than the alternative. The modern air conditioning means that you basically shut all the doors and windows. You turn on an electric air conditioner that that circulates air, indoor air, through a screen that is very, very cold, and you exhaust the heat outside. And in such cases, the owner of the building or the house is very careful about opening doors or windows, because you open a door and all the hot air rushes in and or comes in, and you then wind up spending a fortune on electricity. So the modern refrigerated air conditioning system is a recipe for trouble. So stay away from stores and restaurants and offices and houses that have refrigerated air, unless you're sure that there's nobody there except people that you're sure are not carrying the coronavirus. All right, well, I'll say goodbye. That was too long an afterthought. So have a nice weekend and stay safe. Bye.
Thank you very much.
Thank you.
Thank you for attending. Stop share, end.